We shall continue to discuss the chapter on stress corrosion cracking. In the last class, I started giving the historical perspective of stress corrosion cracking, and then we also highlighted the importance of the stress corrosion cracking for the industrial component safety, how it can impact the safety of the components. And then we looked at the characteristics of stress corrosion cracking, especially in terms of the cracking behavior. And about the characteristics, we said that these cracks are brittle in nature as compared to ductile failures happen in metals due to mechanical loading. And these brittle fractures can be intragranular type, or it can be transgranular type of cracking. Of course, sometimes you can also have a mixed mode of failures, partly intragranular and partly transgranular cracking can really happen. In all these cases, they are brittle and mostly cleavage kind of cracking they appear. So, continuing on the same direction, the next important thing that you would like to know is what are the factors affecting stress corrosion cracking. If you recall, I have given you the Venn diagram, right, wherein we discussed what is stress corrosion cracking. This is SCC, the phenomena that happens, and the factors involved are the metal or the material, the environment, the third are the tensile stresses. So, if you need to understand what are the governing factors, we need to understand in relation to the metals, the metallurgy of the material that is used for a given application, the environment that the material will be exposed to, and the nature of the tensile stresses. Okay. So, all these are going to govern the susceptibility of a material towards stress corrosion cracking. And if you start with, let us start with the tensile stress. Please notice that we are not talking about fatigue or not talking about compressive, we do not talk about the torsion, right, we talk about the tensile stresses. The tensile stresses acting on the material can be classified into two categories. One, it is applied, the other residual stresses, right. The applied stresses are process specific, right, what kind of load you are applying externally. In a chemical reactor, it can come out of the pressure of the reactants and products involved. Okay. And the residual stresses, they reside in the material because of, let us say, the welded component. You weld it, and the weld zone, as you could have a tensile component, and somewhere in the weld component you can also have a compressive component we have. So, there is the residual stresses acting, even you remove all the external loading or stresses onto a component, okay. It could be a cold work. You have done a wire drawing, you have done some kind of sheet metal formed by rolling operations. It can be thermal, can be the thermal stresses acting on the material, or it can also be related to corrosion product accumulation. In the system, right. The corrosion product accumulation can come depending upon the situation. I give a illustration. You guys have some exposure to heat exchangers we have seen, right. In heat exchanger, you would have tube and a tube sheet. You weld it, right, you weld it, or sometimes an expansion joint actually, mostly it is an expansion joint, right. You expand it, and sometimes you weld on one side, normally they weld, where it's facing outside they weld it, and this side is not welded, right. Assume what happens, the liquid goes inside, okay, the environment, penetrate. What can happen? For example, you have iron. Iron can convert into what? It can convert into various corrosion products. One of the product could be iron hydroxide can form, right. The volume of the iron hydroxide is more than the volume of the iron corroded, right. So, volume increase. So, volume increase, right. Now, there is a corrosion products here, and volume increases. What will happen to this tube? The tube will dent, right. It could be a dent, it can happen a dent. Stresses will start acting on that, okay. It can be very high tensile stresses. Now, these stresses can add to the applied stresses, So, when you consider the material against stress corrosion cracking, you need to take care of both the applied stresses and the residual stresses acting on the structure. Now, there is a kind of I would say concept, okay, I would say concept called as threshold stress. Below which stress corrosion cracking does not occur. called sigma TH. There is a symbol sigma TH for that. This arises out of the fact that if you carry out a test in the lab, time to fail versus the applied stresses, right. You apply a stress, you can conduct a simple test, right. I can take a tensile sample and I enclose it in, the cell. I can take the environment here, I can apply stress on the sample, right. This is the environment here, and I can find out the time to failure, simple test, okay, you can do. And if you notice that something like that, you get like this. When I apply a stress, it fails instantaneously, right. What should be the stress at which the metal component fails, a metal fails instantaneously? What is this called? Fracture stress, or what you call in normal term, it is called as ultimate tensile stress, right. But if you lower the stress level in an environment, the time to failure increases, right, isn't it? As you lower the stress, the time to failure increases, and there is a limit, okay, and there is a limit, and this is called as threshold stress, below which metal is not failing. Now this is used in some cases, especially in oil and gas industries. They use this concept of that, okay. But you notice that the threshold stress that we talk about is time dependent, right. What do you mean by that? Suppose here it starts failing, so you know that here it does not fail. What is the time you wait for, right? So generally the time is, say, 1000 hours or 720 hours. If you wait for more, it may start failing, okay. So this is not an ideal parameter, but it is used as an engineering parameter to determine the applicability of a particular material, especially in the oil and gas industries. We will come back to this later, right, and this concept is not used in the nuclear industries, okay, and again I will talk about it later, why it is not used in the nuclear industries. But nevertheless, the literature has you see lots of materials, people give this as a property. Of course, it depends upon the environment. You keep changing environment, the sigma threshold could change. It is not a material property alone, it is also an environmental property, okay. That I think you should be aware of that. Now, for example, I would say this is your 304, 316 and maybe 310, something like that. You can see that it can change. If you are going to use a duplex industrial, things can still go up, and the threshold stress intensity, the threshold stress does not remain constant for all the materials, it can change. Now this this particular thing is very important to understand from the concept of what happens in the stress corrosion cracking. Suppose I apply a component and for a an industry application, how does stress corrosion cracking really work actually? Let us look at the time. With the time, what things are happening? What do really happen with the time? Right? This is the time, and this is, we can say, extension. You take a material and you apply a load, and then expose it to the environment, and you observe. You see that the extension does not happen long time. Have to take place. Okay, at a given load, at a given stress applied stress. So the curve change if the load is if the stress is increasing or decreasing, it could move left and right kind of thing, right? If you look at here, what happens is, you see, generally up to 90% of the time, generally 90% of the time for initiation, for crack initiation. So this is where the crack initiates, and this is where the crack propagates. And this crack initiation is a very interesting thing. Okay. This initiation time, the initiation here involves, it could be a pitting assisted, pitting corrosion assisted one, it could be a crevice corrosion assisted, or intragranular corrosion assisted one, it could be selective leaching. They all called as a precursors, and they are involved in the processes. A pit turns into a crack. An intragranular corrosion turns into a crack, into an intragranular stress corrosion cracking, right? A crevice attack can lead to stress corrosion cracking within the crevice, can happen. Selective leaching also can happen. So these are the factors can assist stress corrosion cracking, and since these are relatively slow processes and quite a bit of time is involved in the crack initiation. So when you talk about stress corrosion cracking control, you should also understand that you can control it by controlling the pitting corrosion, controlling crevice corrosion, intergranular corrosion, selective leaching, all these stuffs. Of course, the metal can leak just with pitting only, it need not be SCC, crevice corrosion can be standalone failure, can happen, but if they are loaded and if the stress levels are beyond the threshold stress levels, yes, they can undergo stress corrosion cracking at later time. So this is a very important and a very interesting thing when you talk about materials development and materials design actually. The other thing that you would like to notice is that, please notice that the crack initiates and grows and finally it is a rupture, right, and this rupture is a mechanical failure. failure of the remaining portion of the specimen or component, right. Suppose I have taken, let us say, about 1 centimeter thick component, it is possible that stress corrosion crack exists up to 70% of the thickness, remaining 30% of thickness it fails by overload. I come to the point later, okay. So it is not necessary that the entire sample, the entire component fails by stress corrosion cracking. This is very important because when you talk about investigation, when you take a failed component, you would not see completely intergranular cracking or transgranular cracking. You will see, yes, there are brittle cracks, but you also see some part of the sample having a ductile fracture. The ductile fracture is coming out of the fact that it is a overload failure. The crack advances, right? It means the crack advances and then it leads to finally overload failure. You know, so you look at this here, right? What is this actually? This one leads to ultimate tensile strength, right? Yes, if you lower the cross section, you keep the same applied load, the stress increases and ultimately that particular segment leads to a mechanical failure. Okay, can happen in practice and it indeed happens in most cases actually. Okay, now that means the two types of design people talk about. The design that takes into account crack initiation and the design that takes into account crack propagation. Right. So what do I mean by a design that takes into account crack initiation? I simply do not accept even a small crack in the component because the metal is considered to be brittle. When a small crack is there and it is going to fracture, so there is a problem, right? There is a problem. So the design that takes care of crack, initiation account, they use the threshold stress as a concept, right? But those design which takes care of the crack propagation, they use the fracture mechanics as a concept. As a criteria for that, right? So that is what they use it. Now, so let us look at how the crack propagates. Again, I am not going to deal with the fracture mechanics, in details, but a bit of exposure to that is useful to see how stress corrosion cracking can affect the crack growth in any given component, right? So if I, what is called as stress intensity factor. Okay, what is stress intensity? And you of course have different modes of loading that you have, and mode 1 of loading, okay, K1 is given by what? Given by y sigma and square root of pi a, right? You might have again studied in maybe in other courses, okay, and K1 corresponds to crack tip stress intensity, and sigma corresponds to applied tensile stress, and A corresponds to crack length, and y is a complex factor. Anybody recollects? It depends upon the geometrical factors. Okay, it depends upon the geometrical. This is a geometrical parameter. So we are not getting into too details about it, but it is, it's, I think it's sufficient for us to get a feel for stress corrosion cracking and crack growth in a given material. Now it's now look at here, depends upon the applied stress, and it depends upon the length of the crack, is related to K1 value, right. Now you know very well that there is something called as K1C. What is this called? Anybody? Yeah, it is toughness. It is a material parameter, right, below which a crack does not grow. Fracture toughness, right, critical stress intensity factor or the fracture toughness, okay, and below which the crack does not really propagate. If I carry out a test to measure the crack growth rate versus crack tip stress intensity, okay, so if I plot A is the length of the crack, and so dA by dt corresponds to crack growth rate and versus the crack tip stress intensity. If I do that in a given environment, of course, you will see that it goes like that. This is called as stage 1 crack growth rate, it's called as stage 2 crack growth rate, and this is stage 3 crack growth rate. What is special about it? What is special about it? The stage 1 and stage 2, the crack growth rates depend upon the crack tip stress intensity, whereas the stage 2 does not depend on the crack tip stress intensity. Rather, it depends on what? So, the stage 2, that K1 dA by dt in stage 1 and stage 3 depends on applied stress intensity or crack tip stress intensity. Stage 2 depends on the nature of the environment. Okay, and not on crack tip stress intensity factor. Again, there are a lot of understanding there. We will not get more details about this. Those who really want to do, there are good papers available, and so we will not right now get into that discussion. Now, let us look at the plot, and this corresponds to what? This corresponds to K1C, and this corresponds to K1SCC. Okay, what is K1SCC? Threshold stress intensity factor for stress corrosion cracking. Please notice that if we have an environment, if you look at this plot, if we have an environment, the crack can grow at a much lower stress intensity level, right, much lower than K1C, right. The K1C is here, it goes much lower than that, and in fact this is they called as subcritical crack growth, right. And so in the presence of environment, you can have subcritical crack growth taking place in the material. That is a disadvantage of the environment actually. Okay, that is something is to be worried about. So the people use these factors, and also people use this is another factor, and this is also, please look at this here, the crack growth rate now does not depend upon stress intensity, and this also is used as an engineering parameter to design the life of the component. So K1SCC and stage 2 crack growth rate. In fact, there are designs just takes care of or uses only the stage 2 crack growth rates. They do not worry about all other things, because if I know what crack growth, below K1C you are not supposed to have any crack growth rate at all. Why is that the crack is growing here? Because of the environment. Okay. Here of course you have a combination of quite a bit of stress intensity and environment, but the role of environment here is much more here, because see there are two things happening. The stress intensity drives the crack first of all, the environment drives the crack more. When you lower the stress intensity, the driving force for crack growth is decreased or increased. When you lower the stress intensity of the crack type, driving force for the crack is decreasing or increasing? Decreasing, right? So it is so if you move over like this, the driving force for the crack is decreasing, crack to grow is decreasing. But what keeps up? The environment keeps up. The environment is making the crack to grow. If there is no environment, in this case the crack growth rate has to be almost, the crack is not supposed to grow at all actually, right? It is not supposed to grow at all. So that is the meaning of this particular plot.
How it will be without the environment actually?
In fact, without the environment, it will start from here only, right? It does not start from here. It will start somewhere here only. It will go from here. It start going here, isn't it? Without the environment, the guy will start here only. In fact, this whole thing will not come into pictures. It will start going somewhere here. Above K1C only, the crack will start even growing. It does not even grow. The crack is there, but does not grow if it is less than K1C, if there is no environment. Okay, so the crack will start. You will see. In fact, it will go like this only. It will go like this or like this. Depends upon tough, other things now. Okay, but it start from here only. Yes. Did I answer the question? Okay. The other parameter that also counts the stress corrosion cracking in general of material is the ductility. The measured ductility, especially in a slow strain rate machines, in a slow strain rate I am not discussing right now. Strain rate test, they use a concept called a loss in ductility. Please again notice all this again time dependent parameters, if you are going to do the experiment at a very low rate, very slow pulling, then the ductility might even decrease quite significantly. So, it is again SCC is a time dependent process, much like creep. The thing is, creep occurs at higher temperature, but here this occurs at it can occur at the ambient temperatures. It is very similar to the creep process, okay, but happening at the ambient temperatures. SCC can occur at higher temperatures. I am not confining this to that. What I am trying to see an analogy of SCC versus creep, it is somewhat similar to creep, which means they are all time dependent phenomena we should take into account. Okay. So we had some idea about, so that means when we have this, then people use a term what is called as SCC susceptibility index. The term that is used, and you might have, if you attended the other course, as I might have discussed in details. Is given as a parameter measured in air minus parameter measured in environment upon the parameter measured in air. This parameter can be anything, it could be ultimate tensile strength measured there, it can be elongation, reduction in area, and it can be if you want to call it, you can call it as K1 SCC versus K1C. Yeah, it's K1C is in air, right? This is in air, this is in the environment measured here. So that's about the role of tensile stresses and how the material is going to behave in terms of the these mechanical parameters in presence of the environment. We saw this briefly. What from the fracture feature of that also, if you can recollect, we said yes, this is brittle, and we also said that in a failed sample in SCC, whether you do it in a laboratory test or in the field, you also have a ductile fracture component in the specimen. Okay, that is happening because see, let's look at it like this. Suppose this is a notch sample, right? It's sample notched, and I have the environment here, and the applied stress is constant. You keep it like that, but as the crack propagates, what happens? The stress increases, right? The actual stress increases on the load bearing member of the specimen, right, and as it moves, then what happens, stress can be equal to, it could be K1C in this case. In a smooth sample it can be UTS value, and so the metal can fail in a ductile manner. So the last ligament that fails would have a ductile component in the material, actually you can see that. The next important thing that we should talk about is the environment. When you say environment, there is always some kind of general feeling that it is specific to environment. It's generally that kind of the concept prevails, and say to give an example, stainless steel, take that, it could fail in the chloride medium, okay. In carbon steel, it could be nitrates, carbonates, like that, nitrates, carbonates, and even phosphates. So what I am giving is just illustration, not an exhaustive list, okay. And you are talking about, let us say, copper based alloys, say the ammonia. Ammoniacal solution is a problem. Similarly, when you talk about in aluminum and magnesium chloride medium, okay. So there are some kind of they are all experimental observations, right, but it appears that SCC need not be confined to a specific environment. The list of environments, they keep adding with the time, okay. In fact, in the nuclear industry, you know that SCC is observed in stainless steels in pure water. The water quality that they use in nuclear industry is extremely very high quality. Even then stress corrosion cracking occurs, but then the time taken for SCC to occur is more, but the pure water can induce stress corrosion cracking on stainless steels at the temperatures, at that pressure, and over a long period. So the specific environment, though people overall talk about it, if you are going to be more technical, I think this may not be totally correct, okay. It can happen in many kinds of environments, but nevertheless environments play a significant role in terms of the life, actually. What are these environments? You say, one, chemical composition, of the environment, right, say chloride, sulfates, phosphates, all these stuffs. Two, the pH of the environment. Third, the temperature. So given a broad picture, right, and broadly you can say this, chemical composition and pH and the temperature, they can influence the stress corrosion cracking susceptibility of the metals. Now when you look at this, broadly speaking, again, let's look at our understanding of stress corrosion cracking. Right now I am not going to get into mechanisms, okay. Let us look at our understanding of the stress corrosion cracking. Now when I apply a stress, tensile stress, you have a crack, a pre-crack is formed here. The crack grows perpendicular to the applied stress, right. The crack grows perpendicular to the stress axis. Stress axis, it is perpendicular to stress axis, it just propagates, it grows. When you have an environment, the crack has to grow the crack tip. If the crack grows, for example, if the crack grows in sideway like that, sideway like this, the stress has to be concentrated at the crack tip. Assume that there is a huge dissolution here, right? Assume there is a huge dissolution, high dissolution. At the crack front, the dissolution rate of the metal is very high. So what will happen? What do you think will happen? I magnify this, and here the huge uniform corrosion, right? It corrodes so much. What will happen there? The crack tip will blunt, crack is no more sharp, blunt. Stress concentration could be significantly reduced from that. So what it means, for stress corrosion to cracking to occur, so for stress corrosion cracking to occur, the crack walls need to be passivated, the film has to be there, so that only the crack tip, the corrosion occurs, the crack starts propagating along the directions, otherwise the SCC will not occur. Assume that I am going to use very strongly corroding acid, SCC will not occur. So the one criteria is that the metals must passivate. If they do not passivate, they do not undergo stress corrosion cracking. The film has to be there in the surface. And say when you take a passivation, right, when you take a passivation, passivity depends on what? You guys already studied, right? It depends on what? It depends upon? It depends on the environment, it depends upon the potential, and depends upon the pH. And what is this diagram called? The Fourier diagram forms certain kind of broad, indication where the stress corrosion cracking can occur for metals. So when we said that the nitrates, the carbonates and phosphates, when you talk about it, they are the ones that passivate the carbon steel, and so they are the ones, they also promote stress corrosion cracking. If there are no applied stresses, I mean they will be very happy, the corrosion rate may be very small, okay, and because there are tensile stresses, the stress corrosion cracking occurs, am I right? Okay. So the passivity is a very important one. Is the passivity is a very important one? Yes, but then if you look at, so then I want to draw this now, say it is your potential, the pH, something like that. I think, I hope you know, this is for ion diagram, right? It is for ion in water. So you have carbonates, and bicarbonates, right, and bicarbonates. You have nitrates and you have phosphates. So these are the ones they phosphates. That means what does it mean? When you take a steel and have water and put a carbonate, bicarbonate, the potential of that solution automatically goes to this particular place and starts passivating. And to phosphates it goes here, in passivates. Put a nitrate, it goes here. So these environments maintain certain pH and the potentials, and so these are the places where you get stress corrosion cracking happening in these steels. People also have shown that in a polarization diagram, SEC region, right? It is a polarization diagram. You see this. They also found that stress corrosion cracking occurs very close to the pitting potential and very close to the active passive potential. These two potential regions, they are happening. So what do you imply from this? What do you imply from this? Passivity is important, but if it is going to show absolute passivity, there will be no stress corrosion cracking. The passivity, so it has to be an unstable passivity or something should disturb the passivity. Okay, so the passivity disruption has to be there. So you take a stainless steel, what does chloride do? The chloride disrupts. What does oxygen do? Oxygen will take the potential towards a higher noble potentials, right? You have chloride, you have oxygen, both of them they make the passive film unstable. You can see that there are pits, and the pits, they become the place of the crack initiation. The pitting occurs. So the chlorides, they do help to damage the film, and when you form a pit, they become stress risers and lead to stress corrosion cracking. We discussed earlier that stress corrosion cracking involves initiation, right? And the initiation process involves, we say pitting is one of the precursor event. You see the pits, they are responsible for stress corrosion cracking. It can happen, and so they are the problems. If this is the case, they found a very nice relationship between stress corrosion cracking and the oxygen content. They call dissolved oxygen versus the chloride level. SEC, no SEC. this we are talking about stainless steels, in thermal and in nuclear power plants. So when you use, so what, how do they generate power? They use water, they create steam, the steam is used to run the turbine. So the water should contain as low as chloride and the oxygen content, so that they do not undergo stress corrosion cracking. It is very critical, okay. And you will see that the oxygen content is in the ppb levels, okay. The chloride also is very untraceable levels of chlorides, okay. So these are the very important things when you talk about the material stability is you know, in SCC. Similarly, you also see this in the cooling waters systems. The heat exchangers at the ambient temperature. See, these temperatures are what? These temperatures are all around about 200 to 280 degrees Celsius, very high temperatures, okay. In the cooling water systems, the temperatures are all in the range of what? In the range of 35 to about 50 degrees Celsius. And you know, cooling water is used, you normally use the drinking water. The chloride content there may be 100 ppm, 200 ppm are going to be there. But then if you are going to use chlorides, and then what happens? The stainless steels become prone to, when I say stainless steel I mean austenitic, please make this change, austenitic stainless steels become susceptible to SCC above 50 degrees Celsius. The other example I just give and then move on, because you know there are several kind of you know, cases we can discuss. This illustration, okay. When it comes to caustic and how it can promote stress corrosion cracking, temperature, carbon steel, no stress relief required. And carbon steel, welds or whatever, okay, stress need to be relieved, or use stainless steels. Here only nickel based alloys. So put it in simple terms, it is necessary for us to understand the environment, you know, before we talk about what will be the right material. When I say environment, I would mean the pH, chemical species, temperature, all the stuffs, okay, are to be known, so that you make a right material selection. Going back, we talked about, let us say you know, cooling water, right. The cooling water, the temperature goes, if the temperature is going to be greater than 50 degrees Celsius, how do the people tackle? They tackle using duplex grade stainless steels, they use that, okay. So, you could find a solution, right. Where you cannot use it, you what do? You bring down the intensity of the environment, in boiler water, 280 degrees Celsius, you can't use duplex stainless steels. So, what happens? You get rid of chlorides, you can get rid of the oxygen content. So, you can have SEC. In the nuclear reactors, what they do, in fact, they add even hydrogen, so that the potential comes down because of the presence of hydrogen in the system. So, you can modify the environment also in order to bring down the stress corrosion cracking tendency of the metals. There are sometimes you get into a very difficult situation in the material selection. It happens in the some industries like a fertilizer industry, for example. The fertilizer industry, say in a heat exchanger, you use ammonia on one side and the chloride on the other side of it, right. How do I choose a material, right? If I have a chloride, then I can choose a copper based alloy, it does not undergo stress corrosion cracking. If it is ammonia, I would go for stainless steel because it is free from stress corrosion cracking in ammonia, right. But I have streams, one side, maybe in the tube, let us say ammonia goes in, on the shell side water goes in and water has got chlorides. So, how do you do that? Okay. So, what people do in this case is they use bimetallic tubes. So, these are all tubes wherein you have two different metals bonded actually, right. One surface you will have brass and inside you will have stainless steel, they are bonded, and so that kind of things are being used. So, what you are trying to look at is, if you know the problem, you can find an engineering solution to the problem, right. So, this is an engineering solution to the problem, right. So, you can overcome the issue without any problems actually at all, okay. And of course, they are expensive, bimetallic tubes are expensive, but that is a solution that you have, so that you can overcome the problem of stress corrosion cracking in the fertilizer industries, okay.
Are these bimetallics bonded together?
Yeah, they just yeah, they bond it. Huh? You can do whatever, I mean it depends upon how the stream looks like, right. You can have copper outside, steel inside, depending upon, of course, the technology that is available, okay, you can do that, but they are simply bimetallic tubes, right. What does it mean? No, it is what it is, right. This may be your stainless steel, this may be your copper based alloy. Yeah, it will go inside. This is one fluid here, fluid 1, and here is the fluid 2. And so, what happens in this case, I will send the ammonia outside, right, and the chloride containing one inside. So, I do not have any stress corrosion cracking issue at all. Any questions so far? Let me go to the next subject, which is in that is the metallurgy of that, okay. It of course, again is very difficult to cover a huge amount of things here, okay, and I will just give a very broad outlook and move, because the metallurgy that you deal with stainless steel is different from than one you deal with aluminum alloys and copper alloys. So, everything goes, okay. So, let us make a very broad discussion, so that you get a feel for what we mean by the metallurgy in relations to the stress corrosion cracking. It could mean the alloy chemistry, could mean the crystal structure, microstructure, okay. When you say microstructure, it means the nature of phases, nature and morphology of the phases, the types of dislocation in the system, grain size, and the nature of the grains. So, they all can happen. Let me start with the alloy chemistry, one example I will give to do that. And I would take here the austenitic stainless steel, or stainless steel I call it, and it is stress corrosion cracking in chloride environment. Time to failure versus the percentage of the nickel content, okay. Goes like that. You know what is the nickel content of this? 8% nickel, almost the one we use as a workhorse, right? 304 has 8% nickel and it is worst. Actually, it's very difficult to separate out alloy chemistry, crystal structure, microstructure, dislocation. They are all intertwined. It's not possible just to separate out, actually, not possible to do that, because if I am going to add nickel, and what happens, the crystal structure changes from BCC to FCC. If I add nickel, then what happens, you will see that the stacking fault energy decreases. So, they are going to have different dislocation structure. So, they are quite intertwined, but still you can try to make some component of what really happens to the SCC from that perspective, that point of view, okay. So, the chemistry of the alloy can happen because at one point of time we said that passivation is a very important one, right. If you are going to add a very high chromium content, if it is going to make the passivation very strong, then the stress corrosion cracking can come down as well, actually, okay. It is possible, can happen, from 304 to 316, and in some cases they do see marginal improvement in the stress corrosion cracking of the alloy, they do see that thing, okay. I think we can continue in the next class.